Um, Welcome, everyone, and thank you for joining us on this deep dive. I want you to start by taking a second and just visualizing the most fundamental concept you probably picked up in your very first high school algebra or physics class.
Oh, this is a great starting point.
Right. Think about that classic, flat, perfectly straight XY axis. The Cartesian plane. You draw a horizontal line, you draw a vertical line, and you map the entire world on it.
It feels completely intuitive.
Exactly. It feels like the baseline of reality itself. But what if I told you that flat line might actually be a ghost? What if the perfectly straight, unbending grid you're picturing in your head right now is nothing more than a highly sophisticated illusion? Essentially, a mental buffer created by our brains to process the speed of light.
It is a genuinely mind-bending premise to open with, but it perfectly sets the stage for the material we're exploring today. We are looking at a highly detailed and deeply mathematical, honestly philosophical framework from our sources that fundamentally questions how we map reality.
Yeah, and we're not just doing abstract math here.
No, not at all. It's a profound reevaluation of how we define simultaneous events in the universe. Like, what does it actually mean for two things to happen at the exact same time?
And so our mission for this deep dive is to explore this theoretical framework because it completely reimagines one of the most famous physics experiments in human history.
The Michelson-Morley experiment.
That's the one. Most of you listening already know the basics of it. The classic L-shaped interferometer setup with the mirrors and the beam splitter. It was originally designed back in the late 19th century to catch the hypothetical ether wind as the Earth moved through space.
Right, and we all know how that story goes. They found absolutely nothing.
Nothing at all. But what our source material does is take that familiar historic setup and it runs it through a completely alien mathematical filter. We're going away from Einstein's traditional ideas of time dilation, and we're venturing into the wild world of complex geometry. We're talking imaginary numbers and something called the spherical cap.
And that shift in perspective is crucial here. The original experiment's failure to detect the Earth's movement threw classical physics into an absolute crisis. The assumption at the time was that if the Earth is moving, light traveling in the direction of that movement should measure differently than light traveling perpendicular to it.
It was a race.
Exactly. It was a race, and one beam should have won, but they always tied.
So let's get into the hard numbers of that race, because the source material provides a very specific modern scenario. If we're looking at this giant L-shaped interferometer, how fast is the source modeling its movement, and what are the physical dimensions we're working with?
Well, the source asks us to imagine the interferometer moving along the x-axis at about 30 kilometers per second.
Which is roughly the Earth's orbital speed around the sun, right?
Correct. And that comes out to 1/10,000th the speed of light. They set the arms of this device to be exactly 10 meters long, and they use a specific light wavelength of 500 nanometers.
Okay, moving fast from a human perspective, but relative to the speed of light, 30 kilometers per second, it's basically a crawl. So if we assume the old, classical, perfectly flat physics model was correct, how much of a delay are we actually looking for?
Meaning, if you wanted those two light beams to perfectly tie the race,
Yeah.
how much would you have to intentionally hold one back?
The calculations give us an incredibly precise, unfathomably small number. To make them arrive simultaneously in a flat, classical universe, you would have to delay the faster beam by exactly 3 times 10 to the negative 16th seconds.
Wow.
Yeah, that is 333 attoseconds. Or to put it another way, 0.3 femtoseconds.
Okay, 333 attoseconds sounds like literally nothing. We're talking about fractions of a fraction of a blink of an eye. Could a couple of guys in the 1880s actually detect a delay infinitely small with just some mirrors and light beam? They absolutely could, and that is what makes the zero result so haunting. Let's translate that tiny fraction of a second into physical reality. That time difference corresponds to a physical difference of 100 nanometers.
Okay.
And because they were using a wavelength of 500 nanometers, that 100 nanometer gap creates what physicists call a 0.2 fringe shift.
Right, which is essentially a 72-degree phase shift in the light waves.
Exactly. When you look at an interference pattern, you see alternating bands of light and dark. A 0.2 shift means those bands would physically slide over by a fifth of their width.
And a fifth of a width is highly visible.
Oh, incredibly visible. The original Michelson-Morley experiment back in 1887 had a visual detection limit of 0.01 fringes.
Oh, wow.
Meaning the expected shift of 0.2 calculated here was 20 times larger than their minimum detection threshold.
So it wouldn't have been a subtle blur. It would have been obvious.
Very obvious. And if we fast forward to the source's inclusion of modern interferometers from 2026, which use advanced optical resonators, their precision is on the order of 10 to the negative 18.
So a shift of this size.
Which is on the order of 10 to the negative 8.
Right. That would be a colossal anomaly.
It would scream off the charts of any modern sensor.
Okay, let's unpack this because this is the crux of the whole mystery that our sources are digging into. In a vacuum, this shift is never observed. The math says there should be a 333 attosecond delay based on the Earth's movement, but reality shows 0 delay. The beams always hit the detector at the exact same time.
This raises an important question, one that gets to the philosophical heart of our deep dive. How do we actually guarantee that events at the start and the end of that 10-meter arm are happening at the same time?
Right.
Because the classic calculation we just discussed assumes classical physics. It assumes the universe is a rigid, flat box.
The Cartesian coordinate system we talked about at the very beginning. The idea that there's a universal, absolute clock ticking away identically everywhere in the universe. If you want to know how long a trip took, you just look at the universal clock, subtract the departure time from the arrival time, and you're done.
But when Michelson and Morley found absolutely no shift, it forced Albert Einstein to challenge that very assumption. Einstein's massive pivot was realizing that you simply cannot assume a moving observer experiences the same now as a stationary observer.
He proposed that because the speed of light is constant for everyone, everywhere, we have to sync our clocks using light signals.
And that revelation led to the groundbreaking concepts of time dilation and Lorentz contraction. The idea that time itself slows down and physical matter and space actually shrink in the direction of motion, just enough to perfectly hide that 333 attosecond delay.
Einstein's model has obviously been the bedrock of modern physics for over a century. But this is where the source material presents a truly fascinating critique of his solution.
It really is fascinating.
The source argues that while Einstein brilliantly fixed the physics, he still relied on the ghost of a flat, one-dimensional x-axis. He didn't get rid of the flat line. He just changed how the ruler shrinks and stretches within that flat line.
The Cartesian ghost is a brilliant way to conceptualize it. It is the lingering assumption that reality is, at its most foundational layer, a flat grid. And you can understand why we cling to it. It's how human beings naturally organize space. It's how we draw maps, how we build houses, how we measure distance. We want the universe to be a neat orthogonal box.
Okay, so here's where it gets really interesting. What if we throw away that flat x-axis entirely? What if the geometry of reality isn't a flat grid that stretches and warps like a rubber band, but something completely different?
The sources introduce a radical alternative model, the complex spherical cap.
The spherical cap.
Yes. Instead of picturing the x-axis from negative 100 to positive 100 as a flat, straight line, imagine it as a projection of a semicircle existing in a complex plane. It is a spherical cap where every single point on that curve is perfectly equidistant from a theoretical center point.
Okay, I'm going to need you to pause and visualize this with me for a second. Because if you have a normal flat line, say a ruler, stretching from negative 100 to positive 100, the center is at 0.
Right.
And the distance to the center from the 0 mark is 0. But the distance from the end of the ruler at 100 to the center is 100. So how can every point on a flat line possibly be perfectly equidistant from a single center point?
Think of the flat x-axis like a piece of string laying on a table. If you pull it tight, it is straight, but the ends of the string are further away from your eyes than the middle of the string.
Right, because of the angle.
Exactly. To make every single part of that string the exact same distance from your eye, you have to physically bow it upward into an arch. You have to curve it. But to do that mathematically without actually shrinking the physical length of the string in the real world, this framework borrows a trick from high-end mathematics.
An imaginary dimension.
Yes.
Imaginary numbers. You've just triggered a collective flashback to high school calculus for half our audience.
I know. I is the letter that ruined math for a lot of people. But stick with me, because here it isn't just a mathematical torture device. It serves a profound physical purpose. Let's look at the math. If distance squared equals x squared plus height squared, say our height is 100, then the distance changes as x changes.
Right, the string gets further away at the edges.
Exactly. To keep the overall radius perfectly constant, which the source calculates at roughly 141.4, the model introduces a complex imaginary axis. Zeta equals I times tau.
So what is tau physically?
This imaginary depth, this tau, dynamically absorbs the time delay. As you move along the x-axis, instead of the physical distance changing, the imaginary depth changes to keep the overall complex radius perfectly constant. It essentially hides the time delay inside a dimension we cannot physically see.
So if I am conceptualizing this correctly, instead of time stretching and space contracting like Einstein proposed, this model suggests the universe is actually a geometric curve.
Yes.
The time delay of 333 attoseconds doesn't require the physical metal of the interferometer to shrink. The delay is completely absorbed by moving through this imaginary dimension. The curvature of space replaces the stretching of time.
Precisely. It turns a problem of time into a problem of shape.
That is wild.
Yeah.
To make this incredibly abstract concept tangible, the source material breaks down a metaphor called the three observers. And I want to spend some time walking through this step by step because it fundamentally changes how you think about perception. Let's start with observer 1.
Observer 1 is the local participant. They are right there in the thick of it, moving fast, say at 0.6 times the speed of light along the x-axis. They are physically riding the beam splitter inside the experiment.
Okay.
Because they are inside the local moving system, they are completely unaware of any time delay. To them, the light goes out, bounces off the mirrors, and comes back perfectly simultaneously. Their local reality feels entirely normal.
That makes sense. If you are on a smoothly moving train, you don't feel the speed. So that is observer 1. Now let's zoom out to observer 2, which the source calls the Maxwell calculator.
Observer 2 is stationary within the broader electromagnetic field. Imagine them positioned far away off to the side of the experiment. Let's say at y equals -100, z equals 0.
Way off to the side.
Right. Because they are stationary and observing from a distance, they see the light arriving from different parts of the experiment at different times, simply due to the sheer distance the light has to travel to reach their eyes. There is an information delay.
Because light, while incredibly fast, isn't infinitely fast. It takes time to cross a gap.
Correct. So observer 2 receives this staggered, delayed information, and here's where the psychology of the Cartesian ghost comes in. Observer 2's brain, or their computer, uses memory to mathematically reconstruct the event. They calculate the delays, correct for the speed of light, and piece together a straight, flat x-axis.
But the source makes a crucial philosophical point here. This flat axis that observer 2 perceives is just a calculated illusion. It is a mental reconstruction after the fact.
That's exactly it.
That is such a wild concept to wrap your head around. The flat reality we think we see is just our brain buffering delayed information to make it look neat and tidy. It makes me think of how we look at the night sky.
Oh, the star map analogy.
Yeah. When you look up at the stars, you see them all projected onto a flat dome, like a ceiling. But in reality, the light from one star might be 4 years old, and the light from the star right next to it might be 4 million years old. Our brain flattens millions of years of depth into a single, flat, 2D picture.
That is a phenomenal analogy. Observer 2 is doing exactly that. They are flattening a complex, time-delayed reality into a simple Cartesian grid. But we still have Observer 3, the describer.
Right, the third perspective.
Imagine this observer positioned high above the whole scene, looking down at the entire system. Say at z equals 1,000.
How does Observer 3 process all this delayed information differently than Observer 2?
Well, what's fascinating here is Observer 3 takes that flat map calculated by Observer 2, but maps it entirely based on an equal degree of past.
An equal degree of past, meaning they want to map points where the information delay is exactly the same.
Yes. If you want to make all points equally delayed from your perspective, you simply cannot use a flat map. Think back to the piece of string on the table. The edges of a flat map are further away from your eye than the center, so the information from the edges takes longer to reach you.
Right.
To make every single point equidistant in time to have an equal degree of past, you have to take that flat map and bow it upward into a dome. You have to physically curve it into the spherical cap.
So bringing this all together, we have this beautiful mind-bending geometry. But how does this actually solve the 333 attosecond problem from the very start of our deep dive? So what does this all mean for the Michelson-Morley zero result without relying on Einstein's shrinking space?
It all comes down to understanding how light moves in this new space. In a complex spherical cap space, light does not travel on a flat plane. It travels along the shortest possible path on a curved surface. In geometry, this is called a geodesic.
Just like an airplane flying from New York to London.
Exactly.
If you look at their flight path on a standard flat map of the Earth, it looks like they are taking a weird, curved detour way up over the poles. But if you look at a globe, you realize that arc is actually a perfectly straight line. It is the shortest possible distance.
Exactly. The flat map distorts the reality of the curved globe. If we connect this to the bigger picture and apply that to our interferometer, it completely redefines our understanding of Lorentz contraction. What we have traditionally perceived for the last century as physical space itself shrinking is, according to this framework, an optical illusion.
An illusion?
Yes.
Yeah.
It is actually just the horizontal, two-dimensional projection of a path that is moving along a curved, higher-dimensional slope.
So if you shine a flashlight up a ramp, the shadow cast on the ground looks shorter than the actual physical beam of light hitting the ramp.
Yeah.
The space itself isn't actually shrinking. We're just looking at a flat, 2D shadow of a curved 3D reality.
That is the perfect way to visualize it. The time delay of 333 attoseconds isn't missing. It is mathematically absorbed by that imaginary depth, that tau variable. Because the light is traveling on this complex, curved geodesic, the physical distance and the time it takes are perfectly balanced by the curvature of the space itself.
Therefore, the light beams arrive at the detector at the exact same geometric moment. Perfect arrival.
Perfect arrival.
The physical result observed in the real world is exactly the same as Einstein's prediction. No fringe shift is ever observed. The experiment ties. But the way it is achieved is entirely different. It is achieved by curving the descriptive geometry of the universe itself, rather than assuming a flat universe where time has to stretch and space has to compress.
The source material rightly refers to this as a potential Copernican revolution of complex geometry. Think about what Copernicus did. He moved us from an Earth-centric, flat understanding of the world to a sun-centric solar system.
Right.
It didn't change the stars in the sky, it changed our geometric understanding of where we stood in relation to them. This framework suggests moving from a flat Cartesian grid-centric physics to a complex, geometrically curved reality. It suggests that our mathematical maps have been hiding the true shape of the territory all along.
What an incredible journey this has been. Let's summarize this for you. We started by looking at a microscopic 333 attosecond discrepancy in a 19th century setup, the Michelson-Morley experiment. We looked at how classical physics couldn't explain it and how Einstein famously fixed it by making time and space flexible.
Right.
But then we explored this completely new, radical framework from our sources. We realized that the flat 3D grid we view the entire world through might just be a mental buffer, a calculated illusion masking a beautifully curved, complex geometric reality based on an imaginary axis.
And this is exactly why diving into these theoretical frameworks is so valuable. It proves that in science, an unsolvable paradox in one framework, like the absolute Cartesian space, might have a perfectly elegant natural solution if you are just willing to change the underlying geometry of your perspective. It reminds us that our most fundamental common sense assumptions about reality are always worth questioning.
It really does make you look at the whole world differently. Which leaves me with a final thought for you to mull over as you go about your day. If our basic perception of a flat, straight line is merely an illusion constructed by our brains to account for the delay of light hitting our eyes, what other obvious flat realities in your everyday life are actually just 2D projections of a much deeper, hidden dimension? Thank you so much for joining us on this deep dive. We love unpacking these mind-expanding concepts with you. Until next time, keep questioning the straight lines.